How do generators produce alternating currents? An AC generator basically consists of a rotor, stator, slip rings, and brushes. The magnet and coil can be either a stator, the stationary component, or a rotor, the rotating component. If the coil is a stator, the magnet will be made a rotor. And if the magnet is a stator, the coil will be made a rotor. The setup is as shown here. We have magnets as our stator, a coil as our rotor. We have the slip rings attached to both ends of the coil, and a brush attached to each ring. Now let's recall Faraday's law of electromagnetic induction, which states that a changing magnetic field induces an electromotive force, EMF, in a conductor. But what's a changing magnetic field? Changing magnetic field refers to a field with varying strength, or changing direction over time. So, if we have a conductor, one way to make the conductor experience a changing magnetic field will be by moving the conductor through the field of magnets. If the conductor stays close to the field or even sits in the field, there will be no EMF induced. Remember, magnetic field doesn't induce EMF, but a changing magnetic field does. Secondly, the rate of the movement of the conductor determines the magnitude of the voltage generated. Also, the polarity of the EMF induced is dependent on the direction of the motion of the conductor, and this is described by the Fleming's right-hand rule. If we have our thumb, first and middle fingers in these positions, our thumb representing the direction of the motion of a conductor, our first finger the direction of the magnetic flux, then our middle finger will represent the direction of current flow through the conductor. In this case, we can see we have our magnetic flux in this direction, while the direction of the current flow is determined by the direction of the force moving the conductor. So, if the conductor moves towards the left, a voltage is induced that enables the current flow this way, and when it moves towards the right, the induced voltage and current flow reverses, armed with that coming back to this. We now understand that as the sides of the coil cuts through the magnetic line of force, it experiences variations in the magnetic field strength. So, we have current flowing through it, whose direction is dependent on the direction in which the coils go through. So the coil going in this direction outwards will experience a current flow in this direction, and the coil moving in the opposite direction experiences a current in this direction. So the continuous rotation of this coil gives us a continuous flow of current, hence electricity represented by this waveform, and is referred to as a sine wave, and the voltage and current generated, described as alternating. But how do we get wires connected to a rotating coil and not get them entangled? Slip rings. We have both wires from both ends of the coil attached to two metal rings, which rotate with them. This wire attached to this ring, this wire attached to this ring, and they all rotates together. Then carbon brushes, which are stationary, but make contact with these rotating metal rings, successfully conducting the electricity generated from the coils to wires effectively. The slip used for the rings refer to the relative motion between the stationary brush and the rotating ring. If we consider the front view of this setup, that is looking from this side, we'll see there's a relationship between the magnitude of the voltage induced on the coil and the angle of rotation of the coil at every single point in time. If we bring in our magnets with the coil at 0 degrees, both surfaces of the coil, with the capacity to cut through the lines of force, do not make contact with the magnetic lines of force. They are outside the magnetic lines of force, and the magnetic lines of force mostly goes through the loop of the coil and doesn't make useful contact with the coil surface. So at this position, we have no induced voltage, and hence no current is generated. When the coil further rotates, it begins to cut through the magnetic lines at an angle. So voltage is induced on both ends of the coil, an equal but opposite polarity, and will increase gradually until the coil is 90 degrees, where it gets the experience of the maximum field strength by reason of his position. So, we notice as this part of the coil cuts upwards, this other part cuts downwards. From the right-hand rule, we can tell current flows outwards from this part of the coil and inwards for this part. The coil continues rotating, and the induced voltage begins to drop, and the coil gets to the 180 degrees position, eventually back to its zero voltage position, but swap sides at this point. Notice that both surfaces of the coil, that's this part and this part that cuts through the lines of force, have gone through it, from one side out to the other side. Okay, so this part has gone from this side out to this side, and this one has gone from this side out to this side, and with further rotation, they are about to go in again, but in the opposite direction. Now, considering Faraday's law of electromagnetic induction, we understand that moving a conductor through a changing magnetic field induces voltage, but from the right-hand rule, we get to understand the induced voltage changes polarity with changing direction of force, hence the change in the direction of the current flow. And that is about to happen, because both sides of the coil are about to re-enter the magnetic field, but from different directions. And once that happens, we get same kind of voltage rise as before, but the different polarity, until it comes back to its starting point, thereby finishing one cycle. Note that the voltage at both sides of the coil while in motion are always equal but opposite. The difference between this voltage is what is experienced across the brushes. In other words, if the coil moves to a position where 3 volts is induced on one side, minus 3 volts will be induced on the other side. The difference between them will be 3 minus 3, which equals 6 volts. This voltage is given across the brushes and will put out a smooth sine wave if considered over time. If we take all this out and try representing the sine wave by a vector, this can be used to analyze the phase of a wave. By phase we mean the position of a wave at a particular instance of time, as it goes through its cycle, especially relative to another wave. And it's referred to as a phasor.